Today, I would like to make an introduction to thermodynamics. Historically, the way in which statistical physics developed was by first observing the macro state of systems of many particles and deriving functional relations between large-scale variables of significant interest to the behavior of the system. This field of empirical study is referred to generically as thermodynamics. Later, as the molecular view of matter gained credibility amongst physicists, an important topic was the justification of these macrostate rules using the known properties of the microscopic molecules. In order to understand this subject, then it is useful to first gain an understanding of the basis and form of thermodynamics. As we noted in previous lectures, the bulk variables for open systems, such as the total energy, are not constant, but instead are subject to usually very small variations, which are termed fluctuations. The assumption behind the study of thermodynamics is that such fluctuations can be ignored because the systems of interest consist of enough molecules to make them negligible. Macrostates can be specified in general by the mean of the bulk variables, which for an equilibrium system are conserved quantities, in the limit that the number of molecules becomes infinite, the fluctuations vanish, and the macrostate specification is the same as specifying the bulk variable. So, consider a closed system consisting of a series of open macroscopic subsystems with equal number of molecules. Assume that each subsystem is in equilibrium internally, but not with each other. As I said last week, each subsystem will have, to a good approximation, a Gibbs distribution, rho equals capital A times e to the power of small a times e, which in the simplest case is specified by the subsystem mean energy. Assume that these mean energies are not all the same. From the Gibbs distribution, we can deduce the entropy of each subsystem using the formula derived 2 weeks ago, that entropy S equals minus mean of logarithm of 2 times pi times reduced Planck constant to the n multiplied by rho of E, what is minus integral dp dq, rho times logarithm of rho minus n times logarithm of 2 times pi times reduced Planck constant. Now, if we further assume, as we did last week, that the joint probability distribution for the entire closed system is the product of all the individual Gibbs distributions, then it follows that the total entropy of the system is the sum of the subsystem entropies. And entropy is an additive macroscopic variable like energy. As time proceeds, it is empirically observed that the total system entropy increases, and in equilibrium, a maximum is achieved in which the mean energies are all equal. This is commonly known as the second law of thermodynamics and is a central organizing principle in thermodynamics. It is important to note that this principle is appropriate only for a closed, isolated system. In an open system, entropy may be added from the system to the environment, resulting in a local decrease, but an overall total increase. The second law is an empirical fact of macroscopic systems, and no violation has ever been observed, apart from the fluctuation effect. So far, we have met two macro variables of interest, namely the energy and entropy. As we noted a moment ago, a system in equilibrium is characterized by having a maximum entropy if we take the second law of thermodynamics as given. Consider now a closed system consisting of two open systems that are in equilibrium with each other. The energy and entropy of each subsystem being denoted by E1, E2, and S1, S2, respectively with E equals E1 plus E2, and S equals S1 plus S2, being the total energy and entropy of the combined system, and energy E is a constant. Consider now the simple case that entropy is solely a function of energy. Si equals S of EI. For entropy S to be maximum, the total system has to be in equilibrium, so we require that ds over dE1 equals 0, since there is only one independent energy variable. However, we have ds over dE1 equals ds1 over dE1 plus ds2 over dE2 times dE2 over dE1. And this is equal to ds1 over dE1 minus ds2 over dE2. The total energy is conserved because ds1 over dE1 equals ds2 over dE2. This argument generalizes to an arbitrary number of systems pairwise in equilibrium with each other, so we get the condition that the derivative of entropy Si with respect to energy Si is constant and equals 1 over the temperature T for all systems to be pairwise in equilibrium. The derivative of entropy with respect to energy is a fundamental marker for equilibrium, and the inverse of this constant is called the temperature T of the total system in equilibrium. Recall now the way we have defined entropy earlier as the Shannon entropy plus a constant, and suppose we take the probability density of the macro state to be the Gibbs distribution, where capital A to the minus 1 of small a equals integral dp dq e to the power of small a times energy E of pq, and this is identical to the partition function z of a. After fixing the parameter a, we obtain that the entropy S equals minus a times expectation energy E with respect to the Gibbs distribution ρ plus logarithm of the partition function z of a plus c. Now we can write that U is identical to the expectation energy E with respect to the Gibbs distribution ρ. That is equal to the partition function z to the minus 1 times integral of dp dq E of pq times e to the power of a times E of pq. Now, the derivative of entropy S with respect to U equals the partition function z to the minus 1 times dz over du minus dA over du times u minus a. And next, we have dz over du that is equal to the integral of dp dq dA over du times energy E of pq times e to the power of a times E of pq, and this is equal to dA over du times z times u. And we obtain, due to the first two terms cancelling, that the derivative of entropy with respect to U equals minus A. And this mean energy U is the thermodynamical energy already discussed. And so we obtain A equals minus 1 over T, which reveals the significance of the particular parameter A in the Gibbs distribution. It is simply minus the inverse absolute temperature. Now, consider two systems not in equilibrium and follow their evolution toward equilibrium, therefore towards states with equal temperatures. The second law insists that the ds over dt equals ds1 over dt plus ds2 over dt, and that is equal to ds1 over de1 times de1 over dt plus ds2 over de2 times de2 over dt, and that is greater than 0. Now, we now invoke conservation of energy between the two systems, so that d1 over dt equals minus d2 over dt, and thus we obtain from above that 1 over t1 minus 1 over t2 times de1 over dt is greater than 0. Let us assume that the first system, for example, has a higher temperature than the second. Then this inequality implies that d1 over dt is less than 0, so that energy must be flowing from the hot system to the cold system as the system equilibrates. Returning now to the entropy, its definition as the Shannon entropy implies that it must be dimensionless. Thus, we see from equation dsi over dei equals constant equals 1 over t, that temperature, the way we have defined it, has units of energy. If the temperature of typical bodies are calculated, we get very small values for the temperature, so it is convenient to introduce effectively a unit of temperature, the degrees Celsius, which is much smaller than a joule. The ratio of the two is given by a constant called Boltzmann's constant. K equals 1.38 times 10 to the power of minus 23 joules per degree. If the temperature is measured using a small unit of energy, namely degrees, then it is conventional often to rescale the definition of entropy by multiplying the original definition by K. And this ensures that all equations derived above work with temperature measured in degrees rather than in joules. The two equilibrating systems previously discussed exchanged only energy. In general, other quantities may be exchanged as well, and if we assume that such quantities are conserved quantities for closed systems, then the Gibbs distribution will involve them as well as the energy. In other words, the entropy will be a function of not just the energy, but also these other invariant quantities. One example is the number of particles, N1 and N2, in the two subsystems. If the systems are able to exchange particles as well, then the entropy becomes a function of the total number of particles as well. Using similar arguments as we did earlier, derive the further condition for equilibrium of our two subsystems using the maximum entropy principle, and we obtain the partial derivative of S1 with respect to N1 equals the partial derivative of S2 with respect to N2. And this equals a constant. And that is minus me over T, where the quantity me has been introduced by this equilibration condition and is referred to as the chemical potential for the system. Another quantity which might be exchanged between subsystems is their volume VI, if we allow the wall between the two subsystems to vary in location. Again, the entropy will be a function of this important variable, and using similar arguments, we obtain that the partial derivative of S1 with respect to V1 equals the partial derivative of S2 with respect to V2, and equals constant equals minus pressure PR over T. The variables T, me, and PR are of central importance to thermodynamics, and their derivation from equations given earlier are called equations of state. Consider now for simplicity the case where entropy is only dependent on energy. In any system, this energy cannot include the bulk kinetic energy of the system, since one would not expect entropy to depend on the velocity of the object being observed due to a principle of relativity. We therefore introduce the concept of internal energy, which is the total energy of a system minus its overall kinetic energy. And we have internal energy I equals total energy E minus kinetic energy Ke, and that equals total energy E minus momentum P squared divided by 2 times mass M. We must now define temperature as dSA over dIA for a given subsystem A. Consider a series of open systems with which together make up a large closed system. The total entropy is then S equals the sum of SA of internal energy IA, where IA equals EA minus momentum PA squared over 2 times mass MA. Now, the fact that the total system is closed means that total momentum and angular momentum must be conserved as well as energy. Thus, we have the sum of momentums PA is constant, and the sum of cross products of the position vectors RA for the particular subsystems and momentums PA is constant. For the entropy to be maximized, we require S maximum subject to the previous 2 constraints. And a necessary condition for this can be derived using a constraint optimization method, Lagrange multipliers. Thus, our optimization function is Lagrangian L equals the sum of entropy SA plus dot product of B and momentum PA plus dot product of C and cross product of position vector RA and momentum PA, where B and C are 3D vector Lagrange multipliers.
Maybe one comment. Yes, so of course here we highly exploit these principles of conservation of total momentum in a closed system. That's coming from third dynamics, Newton dynamics. We also can exploit also the principle of angular momentum conservation. That also can be somehow related with central forces and third Newton dynamics. So that's why we have such three terms in this Lagrange multiplier method. So that's Actually, I will send some more details after this talk. Yeah, so please please move on.
Using the chain rule, we have the partial derivative with respect to the subsystem momentum of subsystem entropy times subsystem energy minus subsystem momentum squared over 2 times subsystem mass, and that is equal to minus subsystem momentum over subsystem mass times equilibrium temperature for all systems T, and that is minus subsystem velocity over temperature T. Returning to the optimization function Lagrangian L and differentiating and setting to 0 gives a minus velocity vector VA over T plus a vector A plus cross product of vector B and the position vector RA equals 0. Or we have velocity vector VA equals U plus cross product of omega and position vector RA, where U is identical to temperature T times A and omega is identical to temperature T times B. U and omega are the same for all subsystems. This equation has the interpretation that in equilibrium, the total system must move as a solid body with velocity U and angular velocity omega. When not in equilibrium, this need not be the case. And that's it.
Yeah, so maybe we can go to some part of discussion. So first of all, at the very beginning, you have mentioned of the presentation, you have mentioned some conditions that are needed for proper thermodynamical description. Actually, I think it's very top, at the very top of presentation. So there is such term as thermodynamic conditions. So the number of particles needs to go to infinity, and the system size also needs to go to infinity. So in a sense, those two conditions are not fully are not satisfied in any physical system, because as you know, always when we consider a physical system, basically we consider a finite system. So there is a very famous example of thermometer with mercury. So the thing is that thermometer, when you measure temperature of your body, you place a thermometer in a special places, but you place it for short time, for limited time. So in a sense, you pre-assume there will be thermodynamic equilibrium achieved between your thermometer that usually has quite small heat capacity and your body that has quite big heat capacity, right? Of course, your body is also not of infinite dimension, infinite size, so number of particles in your body are finite, but still sufficiently high, so you can basically assume that this thermodynamic conditions or thermodynamic limit is partially fulfilled. So then of course it will, in ideal case, when you place thermometer to your body, you have to wait infinitely long time, but in practical term you wait 5 minutes, something like that, and then you achieve that thermodynamic equilibrium was achieved between your thermometer and your body, and then you make you simply see the height of mercury in your thermometer, so you can evaluate the temperature of your body. Also, it's also very much known from paradoxes that glass in your thermometer is also not fully in thermodynamic equilibrium, because, as you know, glass is a liquid with very high viscosity. So when you have mirrors, when you have glass windows that are 100 years old, you see that the thickness of glass is much bigger at the bottom of the glass, and the glass is thinner at the top of the window. This is because how to say, glass is flowing, so that's also quite essential. Yeah, but still, despite the fact that we so in a sense, thermodynamical description is a kind of idealization, but still is a very useful concept. So so that's how it is. Yeah, so maybe I will simply say that, yeah, maybe so maybe I will get some comments from the audience. So do you have any question towards the given topic, maybe to?
So Alexander had to disconnect.
Yeah, I know.
But I have a few questions about the fluctuations. When discussing that the entropy only increases, you talked something about fluctuations being the only, well, the only potential break from the rule.
Yes, but we take this limit, and in a later lecture, I look at the fluctuations, but for
Okay.
now I ignored them.
Yeah, so I can partly answer this question. So actually, it's a very good point. So when you start, this is especially, you know, you never know when so it's as you know, that if you have a quantum system, if you have more than 10 interacting bodies, when you try to consider things rigorously, it's very hard to get any answer from the computations. But some people actually assume that in some limited cases, even a system of 20 interacting bodies can be approximated by thermodynamical description, and then they use the concept of entropy also for quantum systems, which is partly useful. So actually, the smaller the system has the size, the higher the fluctuations are. So that's a quite remarkable feature. So you can partly, and also fluctuations are inherent part of system dynamics. So are not exactly that noise, pure noise that is spoiling our picture. Actually, in fluctuations, there is encoded information about the system dynamics. So fluctuations are part of system dynamics. So that's also very important. So noise is also information. That's under our statement. Yeah. So by very careful analysis of noise, you can get a lot of features of the system. Yeah, so there is also full counting statistics approach to a single electron transport. Maybe one time I will have occasion to talk about this. There's one of my presentation on SlideShare on the topic. So you can, by knowing the Hamiltonian of nanostructure, you can generate somehow, you can have a recipe for statistical description. I would say the very good point of today's presentation was definition of temperature. As you know, this was, yeah, you can go to these cases when there is definition of, yeah, maybe it was a little bit, yeah. So there was, yes, this dSi over dEi is equal to 1 over T. Yeah, it's most proper thermodynamical definition of temperature. And of course, in classical, let's say, in most kind of common sense imagination, this temperature has always positive values. Nevertheless, there are such systems where you can formally also find negative values. Yeah, I will not talk about that, but this is also possible. Yeah, so so that's quite important point. Also, it's at the center of statistical physics, this concept of partition function Z that you have. Go a little bit down. Yeah, you have this, no, maybe it's, yeah, you have this formula where I'm trying to see. Can you go a little bit? Yeah, okay. So you see, you have integral dp dq e to the power. Actually, you can put you have these integrals. So basically, you run over all possible cases, and how to say? So knowing, in principle, knowing the whole the whole dynamics of the system on the micro scale, you can determine z function, and z function later is used as a generating function. So a lot of observables a lot of observable averages you can get by using z function. So it's quite important concept, and perhaps for the system of two interacting electrons onto single electron lines, you shall also be able to derive it. Maybe this is a part of task for me and for Łukasz, we will see. Right. It's open issue how to apply the z function to Dariusz Kotula system under study, under investigation, because simply because, how to say, it's not fully well established what is momentum and position for your case, right, Dariusz? So
Yes, yes.
Maybe position is quite common. Maybe it is.
But momentum is harder.
It's harder. It's harder, and also energy is harder, right? And distinction between energy and entropy is a bit harder, right? But you can try out, and then the question is how to compute z function. Well, I would say you would need to you could do it in oversimplified way, and you have to run over many simulations, and also you can, in principle, you can also numerically compute dz over some variable du or something else by changing the system parameters. In principle, you can do. In principle, you can do, but still, we are walking in landscape of not fully defined quantities, right? I mean, at least we don't have full mapping of our technical problem to statistical physics. So that's something on which we are working right now. Okay. Yeah. Yeah. So actually, that's when you have a cars in the city center, you can use the concept of social force. So when you go with highway, you have tendency to, usually you have a tendency to go in a group. So very far cars that are sufficiently far away, they somehow attract. But if the car starts to approach to themselves, they somehow repel, right? So you don't want to crash. So you have attraction on longer distances and repulsion on smaller distances. This is as with molecules. So you can attempt to describe the motion of the cars in the city center as particles, but actually as cognitive particles. That's what you can do. But actually, there's one. It's okay. So first and second law of dynamics somehow are kind of be reformulated for the case of agent with a social force. Well, let's say acceleration but there's one strong remark. In case of robotic agents or human in a car is like can be treated as a robotic agent. Actually, you can train a humanoid robot to be a driver of a human car, but such car has maximum saturation of a speed and maximum saturation of velocity. So there are some small kind of changes that you need to introduce in Newton law dynamics. And also it's quite characteristic that third Newton law of Newton dynamics is not fulfilled simply because action and reaction. That's not always the case of social force. So this is not exactly fully the physics, but still you can attempt to use the concept of energy, entropy, and temperature in case of cars moving in the city center. So some people does, and then you can introduce the concept of entropy in certain areas of the city or temperature or something. I mean, not just temperature measured by thermometer, but temperature as a concept, which is somehow derived from, as given here, from entropy and energy. Okay. Yes, so I would say the statistical physics is quite a demanding field. So basically, we do have, yes, I mean, so usually we take into considerations two physical systems that are weakly interacting, like superconductor on the left side and on the right side, and there's insulator in between. So this is a Josephson junction. And this interaction Hamiltonian is somehow assumed to be relatively small, as in compared to Hamiltonian of left and right reservoir. Yeah. So okay. So that's it. I would say. Yeah. So is there any more comment on the topic or any question or suggestion? If not, I suggest to finish this presentation.